Picture this. You're standing in what is now Wyoming, but it's 45 million years ago. The air is thick and humid, like stepping into a greenhouse. Through the prehistoric mist, a thunderous crash echoes across the landscape. The ground trembles beneath your feet as something massive approaches, something that dwarfs every land predator alive today. What emerges from the ancient forest defies imagination. Standing 6 feet tall at the shoulder, stretching 12 feet in length, with jaws powerful enough to crush whale bones, Androsarchus represents the pinnacle of mammalian predation. This isn't the world, you know. This is Earth during the age when mammals ruled with unprecedented size and power. But here's the mystery that has puzzled scientists for over a century. How did mammals, creatures that once cowered in the shadows of dinosaurs, transform into giants that dominated every continent? And perhaps more intriguingly, what force was powerful enough to bring down these magnificent behemoths? The story of prehistoric mammals is one of the most dramatic transformations in Earth's history. It's a tale of explosive evolution of creatures so bizarre they seem pulled from fantasy, and of extinction so complete that entire evolutionary lineages vanished forever. From wolf-sized horses with multiple toes to saber-toothed cats with fangs like daggers, from ground sloths the size of elephants to bears that stood 14 feet tall, the prehistoric world teemed with mammalian giants. Today, we embark on a journey through deep time to uncover the rise and fall of these extraordinary creatures and discover what their fate might tell us about our own. Chapter 1. Dawn of the Giants. The asteroid impact that killed the non-avian dinosaurs 66 million years ago didn't just end the Mesozoic era. It opened the greatest real estate opportunity in Earth's history. As the dust settled and the nuclear winter faded, a world of empty ecological niches lay waiting. The stage was set for one of evolution's most spectacular comebacks. In the aftermath of the extinction, the few surviving mammals were small, shrew-like creatures, most weighing less than a modern house cat. They had spent 160 million years living in the shadows of giants, emerging only under cover of darkness to scurry for insects and seeds. But with their reptilian overlords gone, these humble survivors found themselves inheritors of an empty planet. The Paleocene epoch, spanning from 66 to 56 million years ago, marked the beginning of mammals' meteoric rise to dominance. Mammals proliferated in the Paleocene, and the earliest placental and marsupial mammals are recorded from this time. But most Paleocene taxa have ambiguous affinities. Within just 4 million years, a blink of an eye in geological terms, mammals embarked on a stunningly fast evolution. Within just 4 million years, 65 to 61 Maya, amazing new forms evolved to fill the empty ecological roles left by the dinosaurs. This explosion of diversity was unlike anything seen before or since. In mammalian evolution, the early Paleocene world was a warm, humid paradise. Tropical forests stretched to the poles, and there was no ice anywhere on Earth. The devastation of the KPG extinction event included the extinction of large herbivores, which permitted the spread of dense but usually species-poor forests. In this greenhouse world, mammals began their evolutionary experimentation on an unprecedented scale. Multituberculates, a now extinct rodent-like group not closely related to any modern mammal, were the most successful group of mammals in the Mesozoic, and they reached peak diversity in the early Paleocene. Some grew to the size of beavers, sporting unusual teeth that worked like tiny saw blades. These bizarre creatures represented evolution's first attempt at creating large mammalian herbivores, though they would eventually be outcompeted and vanish entirely by the end of the Eocene. But it was another group that would truly seize the moment: the condylarths. The condylarths hoofed animals that were very important members of the Paleocene animal kingdom, included forms that were evolving toward herbivoreness while still retaining insectivorous carnivorous traits of their Cretaceous ancestors. These were the ancestors of all later hoofed mammals, and they began the great mammalian size revolution. Hoofed mammals achieved glorious diversity, though they were still no larger than dog size. However, size restrictions wouldn't last long. As the epoch progressed, mammals grew bolder, bigger, and more diverse. The fossil record from this time reveals creatures that seem almost experimental in nature. They were purgatorious among the earliest primates, scampering through the canopies. Primitive mammalian carnivores, notably the creodonts, a group of cat-like and dog-like animals, appeared, as did large herbivores, ancestral rodents, and the first known supposed primates. One of the most remarkable aspects of Paleocene mammal evolution was the speed at which ecological niches were filled. Large herbivore niches, vacant since the extinction of duck-billed dinosaurs and ceratopsians, were quickly occupied by growing ungulates. Carnivore roles, left empty by the demise of tyrannosaurs and other predatory dinosaurs, were filled by increasingly sophisticated mammalian predators. But mammals weren't the only ones capitalizing on the post-extinction world. The Paleocene. Mammals had to share their world with giant flightless birds of prey, which appeared during the Paleocene and continue through to the Middle Eocene. Standing 2 meters or more in height and weighing in at around 200 kilograms, these large beaked birds were the biggest and fiercest animals on land for some 5 or 10 million years. This created one of the most unusual predator-prey dynamics in Earth's history. Imagine mammals the size of wolves being hunted by birds the size of horses. It was a world turned upside down, where the traditional roles of predator and prey were still being worked out through evolutionary trial and error. These terror birds, as paleontologists call them, dominated the large predator niche, while mammals were still relatively small. The climate during the Paleocene was remarkably stable and warm. Alaska, for example, clearly had broadleafed, evergreen floras that typically grow in tropical forests. As the land has not changed significantly in latitude since the Paleocene, the evidence of these floras is a puzzle. This global greenhouse effect meant that similar tropical ecosystems stretched from pole to pole, creating uniform conditions for mammalian evolution across the planet. Late in the Paleocene, mammalian evolution showed a trend toward larger forms and more varied assemblages. This increase in size was crucial because it set the stage for mammals to challenge the dominance of the terror birds. As mammals grew larger and developed more sophisticated hunting strategies, they began to reclaim the large predator niches that had been temporarily occupied by birds. The Paleocene also saw the establishment of mammalian migration routes that would persist for millions of years. By mid-Paleocene, the ungulates hoofed mammals of initially 5-toed forms became abundant. Prosimian primates, tree shrews, and tarsiers also increased in number. These early mammalian communities formed the foundation for all future mammalian ecosystems. The Deshato fauna from Mongolia contains the remains of the earliest known hare, Eurymilus. And among Paleocene mammal remains from South America are many early representatives of animals that became dominant in subsequent epochs of the Paleogene period. This global distribution of early mammalian forms demonstrates that the Paleocene explosion was truly worldwide in scope. The Paleocene set the foundation for everything that would follow in mammalian evolution. The basic body plans, ecological strategies, and evolutionary trajectories established during this crucial period would echo through the next 60 million years. The rapid diversification demonstrated that mammals possessed an evolutionary flexibility that had been constrained but not eliminated during their long coexistence with dinosaurs. More importantly, the Paleocene proved that mammals could think big. The barriers to large body size that had kept mammals small for over 160 million years had been psychological as much as physical. With the dinosaurs gone, mammals discovered they could grow, and grow they did. But the Paleocene was just the warm-up act. As tropical climates intensified and reached their peak warmth, the stage was set for an even more dramatic transformation. The next chapter would see mammals not just fill ecological niches, but create entirely new ones that had never existed before, ushering in an epoch that would witness the rise of true giants. Chapter 2. The Eocene explosion. Imagine stepping into a time machine set for 50 million years ago. As the temporal mists clear, you find yourself in what appears to be an alien world. Palm trees sway in the breeze, not unusual, except you're standing where London, England exists today. Alligators bask in Arctic sunshine, while early horses, no bigger than house cats and sporting multiple toes, browse in forests that stretch unbroken from the North Pole to the equator. This is Earth during the Eocene epoch, the dawn of modern life, when our planet became a global tropical paradise and mammals began their most spectacular evolutionary experiments. The increase in diversity of mammals that began in the Paleocene continued in the Eocene. The first whales, bats, primitive elephants, and hoofed animals appeared. The Eocene, lasting from 56 to 34 million years ago, represents the golden age of mammalian experimentation, a time when evolution seemed to throw caution to the wind and create creatures that pushed the boundaries of what was biologically possible. The Paleocene transitions to the Eocene by a steep rise in global temperatures that lasted about 130,000 years. This is known as the Paleocene-Eocene. Thermal maximum. Average temperatures rose an estimated 9 to 18 degrees F before cooling back down. This thermal maximum created the warmest global climate of the Cenozoic era, with carbon dioxide levels were approximately 1,400 ppm. The temperature was 30 degrees Celsius with little temperature gradient from pole to pole. In this greenhouse world, mammals exploded into forms that defied imagination. The most marked feature of the Eocene is the origin and radiation of the 16 modern mammalian orders. This wasn't gradual evolution. This was evolutionary eruption on a scale rarely seen in Earth's history. The Eocene is the heyday of the perissodactyls, with more kinds of this ungulate group present than in any other epoch. Among these were the first horses, though you wouldn't recognize them. Hyracotherium, formerly known as Eohippus, stood only 20 inches tall and sported 4 toes on its front feet and 3 on its back. The first horse-like animals lived in the Eocene, but they were the size of dogs and had toes instead of hooves. These were forest browsers, as different from modern horses as wolves are from chihuahuas. But horses weren't the only ungulates experimenting with new body plans. The Brontothers, massive, rhinoceros-like beasts, began their march toward gigantism. Late Eocene perissodactyls from the family Brontotheridae attained huge sizes. The North American megacerops, also known as Brontotherium, reached 2.5 meters. 8 feet 2 in, tall at the shoulders, 5 meters, 16 feet in length, and 3 to 3.5 t, 6,600 to 7,700 pounds in weight. Embolotherium from Asia was equal in size. These weren't just big animals, they were architectural marvels of bone and muscle, with skulls bearing elaborate horns and protuberances that made them look like creatures from fantasy novels. Even more bizarre were the Euntotheres, represented by Euntotherium, which looked like someone had tried to build a rhinoceros from memory and gotten it spectacularly wrong. With a skull 76 centimeters, 30 in long, 1.5 meters, 4 feet 11 in tall at the shoulder, body length of about 4 meters, 13 feet, and a weight up to 2 tons. It was similar to today's rhinoceros, both in size and shape. But unlike rhinos, Euotherium sported 6 bizarre bony protuberances on its skull and massive saber-tooth-like canine teeth. One interesting feature about Euotherium is that it had a concave skull, which means that it dipped inwards instead of outwards like in most other animals. Combined with the thick walls of the skull, this would have reduced the cranial cavity that resulted in a smaller brain size. Perhaps no Eocene mammal captures the epic spirit of evolutionary audacity better than the whales. The transition from land to sea during the Eocene represents one of evolution's most dramatic transformations. Whale ancestors returned to the sea, beginning with creatures like Ambulocetus natans, the walking whale. These early whales straddled two worlds, equally at home on land or in water. With 4 functional legs, but a body clearly adapted for swimming, they demonstrated that evolution could completely redesign a mammalian body plan in just a few million years. The Eocene also witnessed the first experiments with flight among mammals. Bats appeared during this epoch, though their fossil record remains frustratingly sparse. The evolution of powered flight in mammals, achieved independently from birds and insects, represents one of evolution's greatest engineering marvels. These early bats were already sophisticated flyers, suggesting that the transition from gliding to powered flight happened relatively quickly. But perhaps the most impressive Eocene mammal in terms of sheer size was Androsarchus. Although only the skull of Androsarchus mongoliensis has ever been found, researchers infer from the fossil size and evolutionary relationships that the animal was about 6 feet high at the shoulder and 12 feet long, a size that would make Androsarchus the largest known meat-eating land mammal that ever lived. With a skull measuring 83.4 centimeters, 32.8 in long, this beast represented the ultimate mammalian predator. Androsarchus possessed some of the strongest jaws ever evolved in a land mammal, able to bite through large bones if needed. To judge from its immense jaws and the coastal location of the fossils, Androsarchus may have fed on beached primitive whales, shellfish, and hard-shelled turtles, and contemporary large mammals at various periods during its existence. This massive predator wasn't just a land hunter. It was an opportunistic coastal scavenger that could tackle prey of almost any size. The Eocene climate created perfect conditions for mammalian gigantism. In the early Eocene, species living in dense forest were unable to evolve or forms as in the Paleocene. Among them were early primates, whales, and horses, along with many other early forms of mammals. At the top of the food chains were huge birds, such as paracrax. But as the epoch progressed, mammals began to dominate even these apex predator niches dotted in the Miocene. The Antarctic circumpolar current between Australia and Antarctica formed. This disrupted ocean currents worldwide, and as a result, caused a global cooling effect, shrinking the jungles. This allowed mammals to grow to mammoth proportions, such as whales, which, by that time, had become almost fully aquatic. The cooling climate paradoxically enabled even larger mammals to evolve by opening up new ecological opportunities. The diversity of Eocene mammals was staggering. Eocene primates more closely resembled modern forms. Birds also continued to diversify with the appearance of penguins, pelicans, ducks, and gulls. Mammals are represented by a group of Oligocene fossils: the skull of an oreodont, Leptocenia nisha, and a squirrel skull and jaw Schirmes typus. Early primates swung through tropical canopies that extended to what is now Greenland, while primitive elephants trumpeted in forests where the Arctic Ocean now lies. The Eocene's mammalian experiments weren't limited to size. Body plan innovations included the evolution of echolocation in bats, the development of complex trunk musculature in early proboscideans, and the first experiments with aquatic locomotion in whales. Each of these innovations would prove crucial to future mammalian success. continental drift during the Eocene also influenced mammalian evolution. At the beginning of the Eocene, India, which had been moving slowly northward, collided with Asia, and this force started to push up the Himalayan mountains. Australia rifted away from Antarctica and began to move northward. These geological changes created new opportunities for mammalian dispersal while isolating some populations, leading to increased evolutionary experimentation. Mammals like Androsarchus were at the top of the food chain. The late Eocene saw the rebirth of seasons, which caused the expansion of savanna-like areas, along with the evolution of grasses. This climatic shift set the stage for the next phase of mammalian evolution, where open grasslands would favor different body plans and ecological strategies. The Eocene established mammals as the undisputed rulers of terrestrial ecosystems. They had successfully colonized land, sea, and air, achieving a diversity and ecological dominance that surpassed even that of the dinosaurs. But this golden age was about to face its first major test, as global cooling and the emergence of new ecosystems would challenge mammalian giants to adapt or perish. As the Eocene drew to a close, the stage was set for one of the most significant extinction events of the Cenozoic era, an event that would reshape mammalian communities and set the stage for the next chapter in their evolutionary saga. Chapter 3. The Oligocene Transition. The transition from the Eocene to the Oligocene, approximately 34 million years ago, marked one of the most dramatic environmental shifts in Earth's history. This wasn't just a gradual climate change, it was a fundamental reorganization of global ecosystems that would test every mammalian lineage's ability to adapt or face extinction. The greenhouse world that had nurtured mammalian giants for over 20 million years was rapidly giving way to something cooler, drier, and far more challenging. The climate of the Oligocene was mild and temperate in North America. The virtual disappearance of the archaic mammals of the Paleocene marks Oligocene evolution in Europe and North America. But this mild and temperate description masks the revolutionary changes that were reshaping life on Earth. The transition represented nothing less than the end of the tropical paradise that had existed since the extinction of the dinosaurs. The climate, which had been warm and moist in the Eocene, became cool, dry, and seasonal. For the first time in the Cenozoic, Antarctica was covered extensively with glaciers, which lowered sea level. This was the beginning of the modern Ice Age cycle that continues today. Imagine the shock to ecosystems that had known nothing but perpetual warmth for tens of millions of years. Suddenly, winter became a reality, and with it came evolutionary pressures that mammals had never before experienced. By the end of the Eocene, the gap between these two continents was large enough that the circumantarctic current first started flowing. This changed ocean currents around the world and resulted in a global cooling event at the end of the Eocene. This oceanic reorganization created a thermal isolation of Antarctica, allowing ice sheets to form for the first time since the Mesozoic era. The consequences rippled across the globe, fundamentally altering weather patterns, precipitation, and seasonal cycles. Late Eocene, mini-extinction. Many types of large mammals disappear, including all the Euntotheres and Brontothers and Indrocuthers. Primates, once abundant and diverse in North America, disappear from this continent. This extinction event, while not as dramatic as the one that ended the dinosaurs, nonetheless eliminated entire mammalian orders and reshaped terrestrial ecosystems across the planet. The victims were primarily the largest mammals, those magnificent giants that had epitomized Eocene success. The mighty Brontothers, with their elaborate horned skulls and massive bodies, simply vanished. Asteroid impacts are implicated, as two large, buried craters, each half the size of the Yucatan crater tied to the dinosaur extinction, were discovered in the 1990s beneath Chesapeake Bay in the eastern United States and in Russia. They are dated to about 35 Maya. While asteroid impacts may have delivered the final blow, the changing climate had already stressed these ecosystems to their breaking point. Rodent-like multituberculids, which had originated in the Cretaceous, go globally extinct. These bizarre mammals, which had survived the extinction of the dinosaurs and thrived throughout the Paleocene and Eocene, finally succumbed to competition from more advanced mammalian groups. Their extinction marked the end of one of the most successful mammalian experiments in Earth's history. But extinction creates opportunity, and the Oligocene saw the rise of new mammalian dynasties. As temperatures lowered, seasonality increased, grasslands appeared, and the body size of mammals increased. A huge hornless rhinoceros from Asia was the largest land mammal ever to live. This giant was Paraceratherium, and it represented a completely new approach to mammalian gigantism. Paraceratherium was a creature that pushed the boundaries of what was physically possible for a land mammal, standing 18 feet tall at the shoulder and weighing up to 20 tons. It dwarfed even the largest elephants. Yet unlike the robust, heavily built giants of the Eocene, Paraceratherium was surprisingly gracile, with long legs and a neck that allowed it to browse leaves from treetops like a massive giraffe. This was gigantism reimagined for a world of increasing seasonality and resource scarcity. Farther north, temperate forests replaced subtropical forests. Near the end of the Oligocene, savannas, grasslands with scattered trees, appeared. The emergence of grasslands represented one of the most significant ecological innovations in Earth's history. Grasses had existed before, but never as dominant ecosystem components. Their rise would fundamentally alter mammalian evolution, favoring new body plans, digestive strategies, and social behaviors. As forests diminished, some animal species adapted and became grazers. Many species could not survive the change in climate and perished. The transition from browsing to grazing required comprehensive anatomical reorganization. Teeth had to become higher crowned to handle the silica-rich grasses. Digestive systems needed to evolve complex fermentation chambers to extract nutrients from low-quality plant material. Bodies had to become adapted for sustained running across open plains. Many other new forms evolved that could cope with the savanna's limited hiding places. Early forms of monkeys, dogs, cats, rhinoceroses, pigs, and camels were present. These weren't just the ancestors of modern groups. They were pioneer species colonizing entirely new ecological niches. The open savanna environment favored different survival strategies than the closed forests of the Eocene. Speed became more important than strength, endurance more valuable than power, and cooperation often trumped solitary behavior. The evolution of cursorial running mammals represents one of the Oligocene's most significant innovations. As forests gave way to grasslands, the ability to run fast and far became crucial for both predators and prey. This led to remarkable convergent evolution, with multiple mammalian lineages independently developing similar adaptations. Longer legs, modified foot bones, enlarged hearts and lungs, and streamlined body plans. Dogs began their evolutionary journey toward becoming the ultimate pursued predators. Early members of the dog family developed endurance hunting strategies that would eventually make them among the most successful carnivores on Earth. Their evolution was intimately tied to the rise of grasslands and the hoofed mammals that grazed upon them. Cats, meanwhile, took a different approach. Rather than becoming endurance hunters like dogs, early felines evolved as ambush predators, specialized for explosive power and precision strikes. The contrast between these two carnivorous strategies, endurance versus power, pack versus solitary hunting, would define terrestrial predation for the next 30 million years. The late Oligocene, the caviomorph rodents, for example porcupines, capybaras, Chinchillas, guinea pigs, etc. invaded South America from the north. This colonization event demonstrates how the Oligocene's environmental changes created opportunities for long-distance dispersal. As sea levels dropped due to Antarctic glaciation, land bridges emerged that had been submerged for millions of years, allowing mammalian groups to colonize new continents. The Oligocene also saw crucial developments in mammalian intelligence and social behavior. The environmental challenges posed by increasing seasonality and resource scarcity favored mammals with greater behavioral flexibility. This period saw the evolution of more complex social structures, enhanced learning abilities, and sophisticated communication systems. These cognitive advances would prove crucial for surviving future environmental challenges. Continental movements during the Oligocene continued to reshape biogeography. More of North America was dry land than in the preceding Eocene epoch. The Gulf Coast remained flooded, but the Atlantic coast north of South Carolina was dry land during most of this time. India pushed farther into Asia. South America separated from Antarctica, and Australia continued to move away from Antarctica. These geographical changes isolated some populations while connecting others, creating a complex mosaic of evolutionary opportunities and constraints. Volcanic activity also played a role in Oligocene mammalian evolution. There was a significant increase in volcanic activity in Europe and in North America. Yellowstone National Park is a remnant of this activity. During the Oligocene, volcanoes erupted in the San Juan Mountains of Colorado and the Absaroka Mountains of Wyoming, where unrelated volcanism still persists in Yellowstone National Park. These volcanic episodes may have contributed to climate cooling by injecting sulfur compounds into the atmosphere, accelerating the transition away from greenhouse conditions. The fossil record of Oligocene mammals is particularly rich in North America's White River region. The great erosion of the Rocky Mountains was responsible for the deposition of the fossil-rich White River group clay and sand over large areas of western Nebraska and northeastern Colorado and parts of Wyoming and the Dakotas, including Badlands National Park in South Dakota. These deposits have yielded some of the most complete mammalian fossils ever discovered, providing detailed insights into how mammals adapted to the changing world. By the end of the Oligocene, mammalian communities looked fundamentally different from those that had dominated the Eocene. The giants of the greenhouse world had been replaced by more modest-sized mammals, better adapted to cooler, more seasonal climates. Grasslands were expanding across continental interiors, setting the stage for the next phase of mammalian evolution. The Oligocene had successfully filtered mammalian diversity through one of the most significant environmental challenges of the Cenozoic era, and those lineages that survived would be well-positioned to exploit the opportunities of the coming Miocene world. The transformation was complete. Mammals had evolved from tropical forest dwellers into adaptable generalists capable of thriving in diverse environments. This evolutionary flexibility would serve them well as the climate continued to cool and new challenges emerged on the horizon. Chapter 4. The Miocene Golden Age. If the Oligocene was a time of transition and adaptation, the Miocene epoch, lasting from 23 to 5.3 million years ago, represented the absolute pinnacle of mammalian diversity and success. The entire Miocene is the golden age of mammals, with an astounding diversity of mammalian species on land. Never before or since have mammals achieved such spectacular variety in size, form, and ecological strategy. This was an epoch when evolution seemed to be conducting a grand experiment in mammalian possibilities, creating creatures that pushed every conceivable boundary of what it meant to be a mammal. The Miocene was a time of warmer global climates than those in the preceding Oligocene or the following Pliocene. The expansion of grasslands is correlated to a drying of continental interiors as the global climate warmed. And it is not surprising that the hoofed animals continued their rapid evolution during the Miocene. This warming trend, while not as extreme as the Eocene greenhouse, provided the perfect environmental backdrop for mammalian experimentation and expansion. The Miocene climate created a world of vast grasslands punctuated by woodlands and forests. Mosaic of habitats that supported an incredible diversity of ecological niches. The global climate warms, but it is still very dry, providing ideal conditions for modern grasses to flourish. Grasses cope well with drought and are superbly adapted to survive mammal grazing because the growing cells of grasses are concealed at the base, not exposed at the tip. This grass-mammal partnership became one of the most successful ecological relationships in Earth's history, with each group driving the evolution of the other. Some mammals co-evolved high-crowned teeth to withstand abrasion from silica granules embedded in grasses. This evolutionary arms race between grasses and grazers produced some of the most sophisticated dental machinery ever evolved. Horses developed continuously growing teeth that could handle a lifetime of grinding tough grass. Proboscideans evolved multiple sets of replacement molars, discarding worn teeth like a conveyor belt of chewing surfaces. These innovations allowed mammals to fully exploit the expanding grassland ecosystems. North America during the Miocene was a continent-sized laboratory for mammalian evolution. Camels, still confined to North America, diversify into forms that resemble African gazelles and giraffes. Many kinds of peccaries fulfill the pig niche in North America. The diversity was staggering. Imagine prairies filled with camel giraffes browsing alongside pig-like peccaries of every conceivable size and specialization. This represents one of evolution's most spectacular demonstrations of adaptive radiation within established mammalian lineages. These are examples of convergent evolution. Earth itself is calling forth the gazelle form, the giraffe form, the pig form, and will work on whatever lineage is available. This phenomenon reveals a fundamental principle of evolution. Similar environmental challenges consistently produce similar biological solutions, regardless of the ancestral starting point. The Miocene provided perfect conditions for observing this principle in action on a global scale. The sheer size of some Miocene mammals defied comprehension. Dinotherium, an elephant relative, stood 12 feet tall with bizarre downward curving tusks that functioned like grappling hooks for stripping bark. Gomphotherium, another proboscidean, sported 4 tusks, 2 pointing forward and 2 pointing down, creating what must have been one of the most intimidating faces in mammalian history. These weren't just large animals. They were evolutionary experiments in alternative elephant architecture. But perhaps no Miocene mammal captures the epic spirit of gigantism better than Paraceratherium, the largest land mammal that ever lived. While technically spanning from the Oligocene into the early Miocene, this massive rhinoceros reached its evolutionary peak during the Miocene's warm, stable climate. The largest known Deinoceratodon was Eobasileus with skull length of 102 centimeters, 40 in, 2.1 meters, 6 feet 11 in, tall at the back, and 1.5 meters, 4 feet 11 in, tall at the shoulder. Yet even Eobasileus was dwarfed by Paraceratherium, which stood 18 feet at the shoulder and weighed as much as 4 elephants. The diversity of the shoulder and waist of the shoulder and weighed as much as 4 elephants. The diversity of Virolisvor, just 18 feet at the shoulder. Miocene carnivorans was equally impressive. The period saw the evolution of multiple saber-toothed lineages, each taking a different approach to hypercarnivory. Barbarophilis developed massive, flattened canine teeth designed for delivering precision killing bites to megafauna. Meanwhile, the true cats were experimenting with their own saber-toothed forms, leading to the evolution of Machairodus, ancestor to the famous Smilodon. The Miocene also witnessed the rise of the bear dogs, massive carnivorous mammals that combined the power of bears with the hunting instincts of dogs. Amphibian, the largest of these, stood 4 feet at the shoulder and weighed as much as a grizzly bear, yet retained the cursorial adaptations of a pursuit predator. These were pack hunters capable of bringing down the largest herbivores of their time. At the water's edge, the bear family sends ancestors of seals back into the sea. This transition from terrestrial to aquatic life represents another example of Miocene evolutionary audacity. Early pinnipeds like Eneliarctos retained 4 functional limbs, but had already developed the streamlined bodies and specialized circulatory systems needed for diving. Their evolution paralleled that of whales millions of years earlier, demonstrating that the transition from land to sea is a recurring theme in mammalian evolution. The Miocene marked the emergence of truly modern whale communities. By this time, baleen whales had evolved their sophisticated filter-feeding apparatus, allowing them to exploit the rich plankton blooms of the cooling oceans. Toothed whales developed echolocation to hunting precision never before achieved by aquatic predators. The ocean had become as mammal-dominated as the land. South America, during the Miocene, was an isolated continent that had been conducting its own evolutionary experiments for over 30 million years. The result was a mammalian fauna so bizarre it seemed to belong to an alien world. Thylacosmolus, a marsupial predator, had evolved saber teeth entirely independently of placental carnivores, a stunning example of convergent evolution. Giant ground sloths like Megatherium ancestors were beginning their march toward gigantism, while bizarre hoofed mammals called nodongulates filled niches occupied by horses and rhinoceroses on other continents. The diversity of Miocene horses alone illustrates the epoc's evolutionary exuberance. 3-toed horses like Merychippus grazed alongside more primitive browsers, while miniature horses no bigger than dogs occupied forest niches. Some horses evolved into giants like Dinohippus, standing as tall as modern Clydesdales. The horse family tree during the Miocene resembled a complex bush rather than the linear progression often depicted in textbooks. Proboscideans reached their peak diversity during the Miocene. In addition to the familiar elephant lineages, the epoch saw the evolution of shovel-tusked mastodons like Amebalodon, whose flattened lower tusks functioned like earth-moving equipment for stripping aquatic vegetation. Stegodon developed massive, closely spaced tusks that created an impenetrable barrier in front of the skull. These weren't evolutionary dead ends. They were successful specialists that thrived for millions of years. The Miocene climate fostered the evolution of mammalian migration patterns that rivaled those of any other geological period. Vast herds of horses, camels, and rhinoceroses moved seasonally across the expanding grasslands of North America. These migrations created a dynamic ecosystem where predator and prey populations fluctuated in complex cycles, driving continued evolutionary innovation. Rodents underwent their own spectacular diversification during the Miocene. Giant beavers, like castoroids, grew to the size of bears, building dams and engineering waterways on a scale that dwarfs anything achieved by modern beavers. Porcupines evolved into tree-dwelling specialists, while prairie dogs developed complex social systems, rivaling those of primates. The success of rodents during the Miocene demonstrates that evolutionary triumph wasn't limited to large, charismatic megafauna. The period also saw crucial developments in mammalian intelligence and social complexity. Many Miocene mammals lived in large herds with sophisticated social hierarchies. Early elephants developed complex family structures and matriarchal societies that characterize modern species. Primate communities in Africa and Eurasia were experimenting with tool use and complex communication systems that would eventually lead to human evolution. Continental connections during the Miocene created opportunities for mammalian dispersal on an unprecedented scale. The Bering Land Bridge allowed Asian and North American faunas to intermingle freely, while temporary land connections between Africa and Eurasia facilitated exchanges between these continents. These dispersal events created evolutionary pressure that drove innovation and adaptation across mammalian communities worldwide. The volcanic activity of the Miocene, while sometimes destructive, also created new opportunities for mammalian evolution. The Columbia River flood basalts in North America initially devastated regional ecosystems, but ultimately created new habitats as the lava flows cooled and weathered. Mammals proved remarkably adept at recolonizing these disturbed areas, often evolving new adaptations in the process. Marine mammals reached unprecedented diversity during the Miocene. Early dolphins were experimenting with echolocation systems of extraordinary sophistication. Baleen whales evolved the largest body sizes in mammalian history, with some species approaching the dimensions of modern blue whales. The ocean had become a three-dimensional grassland where mammalian grazers filter-feeding whales harvested vast crops of microscopic plankton. By the late Miocene, mammalian communities had achieved a stability and diversity that seemed sustainable indefinitely. Ecosystems were mature and complex, with intricate food webs connecting hundreds of mammalian species. The evolutionary innovations of the epoch had created mammals capable of thriving in every conceivable terrestrial and marine environment. Yet, even as the Miocene Golden Age reached its zenith, subtle changes were beginning to affect global climate systems. The gradual cooling that would define the Pliocene was already underway, and with it came new evolutionary pressures that would test every mammalian lineage's ability to adapt. The Golden Age was about to face its greatest challenge as the world began its inexorable slide toward the ice ages that would reshape mammalian evolution once again. The Miocene had demonstrated the full potential of mammalian evolution. Never again would mammals achieve such diversity, such ecological dominance, or such spectacular examples of evolutionary innovation. It was truly the pinnacle of mammalian success, a golden age that would be remembered as the high point of our planet's experiment with warm-blooded, intelligent life. Chapter 5. The Rise of Predators. The evolution of mammalian predation during the Cenozoic era represents one of nature's most sophisticated arms races. From the modest insectivores of the Paleocene to the massive saber-toothed cats of the Pleistocene, predatory mammals developed hunting strategies and anatomical specializations that pushed the boundaries of what was biologically possible. This evolutionary theater of predator and prey would produce some of the most iconic and terrifying mammals ever to walk the earth. The story of mammalian predation begins modestly in the post-dinosaur world. Early Paleocene carnivores were small, generalized hunters that fed primarily on insects, small vertebrates, and occasionally carrion. These primitive predators lacked the sophisticated killing apparatus that would characterize later carnivores. They were opportunists, taking advantage of the ecological vacuum left by the extinction of large theropod dinosaurs. The first true mammalian carnivores appeared during the late Paleocene and early Eocene. The creodonts, primitive mammalian carnivores, notably. The creodonts, a group of cat-like and dog-like animals, appeared, as did large herbivores, ancestral rodents, and the first known supposed primates. These early carnivores represented evolution's first serious attempt at creating specialized mammalian killing machines. Creodonts were remarkable creatures that combined features we now associate with both cats and dogs. Some, like Oxyana, were built like oversized badgers with powerful jaws designed for crushing bone. Others, such as Patriophilus, resembled giant weasels with elongated bodies perfect for pursuing prey into burrows and crevices. The largest creodonts, like Sarcastodon, grew to the size of grizzly bears and possessed skulls over 3 feet long. But the creodonts were just the opening act. The Eocene epoch witnessed the emergence of Androsarchus, a predator so massive it redefined the possibilities of terrestrial carnivory. Although only the skull of Androsarchus mongoliensis has ever been found, researchers infer from the fossil size and evolutionary relationships that the animal was about 6 feet high at the shoulder and 12 feet long, a size that would make Androsarchus the largest known meat-eating land mammal that ever lived. Androsarchus possessed some of the strongest jaws ever evolved in a land mammal, able to bite through large bones if needed. The skull, measuring 83.4 centimeters, 32.8 in long, was equipped with teeth designed for both cutting meat and crushing bone. This wasn't just a predator, it was a mobile bone processing factory, capable of extracting every possible calorie from its kills. To judge from its immense jaws and the coastal location of the fossils, Androsarchus may have fed on beached primitive whales, shellfish, and hard-shelled turtles, and contemporary large mammals at various periods during its existence. The evolution of Androsarchus illustrates a crucial principle in predator evolution. As prey animals grow larger, predators must evolve even more powerful killing mechanisms. The Eocene world was filled with massive herbivores like brontothers and euntatheres, and Androsarchus represented nature's answer to this challenge. Its massive skull and powerful jaw muscles could deliver bite forces that would make him modern. Crocodiles seem weak by comparison, as the Oligocene transition eliminated many of the largest herbivores. Predator evolution took a different direction. The climate, which had been warm and moist in the Eocene, became cool, dry, and seasonal. This environmental shift favored predators that could pursue prey across open landscapes rather than ambush them in dense forests. The result was the evolution of cursorial, running carnivores that could maintain high speeds over long distances. The dog family began its evolutionary journey toward becoming the ultimate pursuit predators during this period. Early canids developed the endurance hunting strategies that would eventually make them among the most successful carnivores on Earth. Their evolution was intimately tied to the rise of grasslands and the hoofed mammals that grazed upon them. As prey animals developed greater running speed, dogs evolved enhanced stamina, pack hunting behaviors, and sophisticated communication systems. Cats took a fundamentally different evolutionary approach. Rather than competing with dogs in the endurance hunting niche, felines specialized as ambush predators focused on explosive power and precision strikes. The earliest true cats appeared during the Oligocene, but it was during the Miocene that they began their most famous evolutionary experiment, the development of saber-teeth. The evolution of saber-toothed cats represents one of the most remarkable examples of convergent evolution in mammalian history. Based on mitochondrial DNA sequences extracted from fossils, Megarodontanes diverged from the ancestors of living cats around 20 million years ago, with the last surviving Megarodont, genera Homotherium and Smilodon, estimated to have diverged from each other about 18 million years ago. This means that saber-toothed cats evolved their characteristic weaponry independently multiple times, suggesting that enlarged canine teeth provide significant advantages for hunting large prey. The Megarodontine originated in the Middle Miocene of Europe. The early felid Pseudalurus quadridentatus showed a trend towards elongated upper canines and is believed to be at the base of the Megarodontine evolution. From these humble beginnings, saber-toothed cats would evolve into some of the most specialized predators ever created by natural selection. Traditionally, 3 different tribes of Megarodontines were recognized: the Smilodontini with typical Dirk-toothed forms, such as Megantherion and Smilodon, the Macaradontini or Hopmotherini with scimitar-toothed cats, such as Macharodus and Homotherium, and the Metallorini. Each tribe represented a different solution to the challenge of killing large prey with elongated canine teeth. The scimitar-toothed cats, exemplified by Homotherium, developed shorter, more curved canines that functioned like slicing blades. These predators were built for pursuit hunting, with longer legs and more cursorial body proportions than their dirk-toothed relatives. Homotherium could pursue prey across open landscapes, then deliver precision slicing attacks to major blood vessels. The dirk-toothed cats, culminating in the famous Smilodon, evolved massively elongated canines that functioned like organic daggers. Smilodon was one of the last surviving Macharodonts alongside Homotherium. Smilodon lived in the Americas during the Pleistocene to early Holocene epoch, 2.5 Maya, at latest 8,200 years ago. 3 species are recognized today: S. gracilis, S. fatalis, and S. populator. The 2 latter species were probably descended from S. gracilis, which itself probably evolved from Megant, EREO, and the largest species, Smilodon populator, was truly a monster. Smilodon populator was the largest saber-toothed cat, popularly known as the saber-toothed tiger. S. populator was a fierce predator, about 3 meters long and 1.25 meters tall. Smilodon species weighed anywhere from 110 gracilis, 400 populator kg. This made it significantly larger than any modern big cat, yet it possessed canine teeth over 7 inches long. The killing technique of saber-toothed cats has been the subject of considerable scientific debate. After pinning its victim down with its powerful front legs, Smilodon would use its powerful neck muscles to drive its saber teeth into the neck of its prey. Some scientists, however, disagree with this and believe it targeted the belly of its prey. The evidence suggests that saber-toothed cats were precision killers that targeted specific anatomical weak points rather than relying on the sustained biting and shaking techniques used by modern big cats. Unlike living big cats, which generally clamp the muzzle or throat of prey to asphyxiate them, saber-toothed Macharodontines are thought to have killed prey using a bite to the neck once immobilized. This required extraordinary anatomical specializations. Smilodon had jaws that could open to 120 degrees, while on the other hand, today's lions can only open their jaws at 65 degrees. This massive gape was necessary to clear the enormous canine teeth when biting. The evolution of saber teeth came with significant trade-offs. Its jaws were weak as a result of its long canines. Its bite strength was comparable to a large dog and much weaker than that of a lion. This meant that saber-toothed cats had to rely entirely on their specialized weaponry rather than brute jaw strength. They were living examples of evolution's tendency to create highly specialized solutions to ecological challenges. The success of saber-toothed cats during the Pliocene and Pleistocene demonstrates the effectiveness of their specialized hunting strategy. They coexisted with modern cats for millions of years, suggesting that both approaches to carnivory were viable. Saber-toothed and conical-toothed felids had formerly coexisted for more than 1 million years, indicating that specialization and generalization could both succeed in the complex ecosystems of the late Cenozoic. But saber-toothed cats weren't the only mammalian predators reaching gigantic proportions during the Pleistocene. The giant short-faced bear, Arctodus simus, was the largest carnivorous mammal to ever roam North America. Standing on its hind legs, an adult giant short-faced bear boasted a vertical reach of more than 14 feet. The most striking difference between modern North American bears and the giant short-faced bear were its long, lean, and muscular legs. The short-faced bear was huge and had much longer legs than modern bears relative to the body, which has given rise to the idea that it was a cursorial predator, meaning that it ran after prey. This represented a completely different approach to large mammalian predation rather than the ambush tactics of saber-toothed cats or the pack-hunting strategies of dire wolves. Short-faced bears were solitary pursuit predators capable of running down almost any prey animal. South America developed its own unique predatory mammals during its long isolation. The largest terrestrial mammalian predator, as well the largest known bear and terrestrial carnivore of all time, was Arctotherium angustidens, the South American short-faced bear. A humorous of angustidens from Buenos Aires indicates that the males of the species could have weighed 1,588 to 1,749 kilograms, 3,501 to 3,856 pounds, and stood at least 3.4 meters, 11 feet, tall on their hind limbs. This massive bear dwarfed even its North American relative, representing the ultimate expression of Ursid gigantism. The diversity of Pleistocene predators extended beyond just the famous megafauna. Dire wolves roamed every inch of North America, from the frozen Canadian north down through Mexico, and thrived in every imaginable ecosystem, from boreal forests to grassland plains to tropical wetlands. Like gray wolves, dire wolves hunted in packs of 30 or more and fed on large prey like mammoths, giant sloths, and Ice Age horses. Dire wolves represented a different evolutionary solution to pack hunting than modern wolves. They were more robust, with larger heads and more powerful jaw muscles designed for processing bone and tough hide. Their social structures may have been even more complex than those of modern wolves, allowing them to coordinate attacks on prey much larger than themselves. The success of these diverse predatory strategies demonstrates that the Pleistocene world supported a level of carnivore diversity that has never been equaled. From solitary ambush predators to pack hunters to pursuit specialists, mammalian carnivores had evolved solutions to virtually every conceivable hunting challenge. This diversity would prove to be both their greatest strength and, ultimately, their fatal weakness as the world entered the final phase of mammalian gigantism. Chapter 6: Giants of the Ice Age, the Pleistocene Epoch. Spanning from 2.6 million to 11,700 years ago, represents the final chapter in the age of mammalian giants. Commonly called the Ice Age, this period witnessed the evolution of the largest, most spectacular mammals ever to walk the earth. These were creatures that pushed the physical limits of what was possible for terrestrial life, creating a world where giants ruled landscapes from the Arctic tundra to South American grasslands. Yet this epoch of unprecedented mammalian magnificence would also become their tomb, as forces beyond their control conspired to bring down the mightiest animals our planet has ever known. The Pleistocene's climate was cyclical, characterized by the advance and retreat of continental ice sheets. These cycles of glacials, cold periods, and interglacials, warmer periods, were driven by variations in Earth's orbit that altered solar radiation. During peak glacial periods, ice covered an estimated 30% of the Earth's surface, with glaciers over a mile thick in parts of North America, Europe, and Asia. This buildup of ice locked away large amounts of water, causing global sea levels to drop by as much as 390 feet, 120 meters. This dramatic restructuring of global geography created vast new landscapes for mammalian colonization. The Bering Land Bridge connected Asia and North America, allowing unprecedented faunal exchanges between continents. Britain was connected to continental Europe, and what are now islands became part of larger continental masses. These geographic connections would prove crucial for the dispersal of Ice Age megafauna across the globe. The mammoth steppe that stretched across northern Eurasia and Alaska during glacial periods supported the largest mammalian communities in Earth's history. This was no ordinary grassland. It was a hyper-productive ecosystem that could sustain enormous herds of massive herbivores. The cold, dry climate and deep permafrost created conditions unlike anything in the modern world, supporting grasses and herbs with nutritional content far exceeding that of contemporary vegetation. The Pleistocene landscape supported large animals, known as megafauna, including the woolly mammoth, Mammothus primigenius. A relative of modern elephants, mammoths were adapted to the cold, standing up to 12 feet tall and weighing over 6 tons. They had a thick coat of shaggy hair, insulating, fat, small ears to prevent heat loss, and curved tusks for defense and foraging. Mammoths roamed the steppe in herds, feeding on grasses and sedges. Woolly mammoths were perhaps the most iconic of all Ice Age giants, and their evolution demonstrates how dramatically mammals could adapt to extreme environmental conditions. Their double-layered coat consisted of long guard hairs up to 3 feet in length, covering a dense undercoat of shorter, softer fur. This insulation was so effective that mammoths could maintain their body temperature in conditions that would be fatal to modern elephants. The curved tusks of woolly mammoths were multi-purpose tools that could reach lengths of 16 feet in males. These tusks functioned as snowplows for clearing feeding areas, weapons for defense and dominance displays, and even as support posts when the massive animals needed to rest in deep snow. The wear patterns on mammoth tusks reveal sophisticated behaviors, including the ability to determine wind direction and seasonal migration patterns. Mammoths spread everywhere in Ice Age North America, ranging from Canada down to Honduras. Nearly all mammoths and mastodons were wiped out in the Great Megafauna Extinction 10,000 years ago, but archaeologists have dug up remains showing that lone bands of mammoths still roamed Arctic islands as recently as 4,500 years ago. There were mammoths living down to the time when the Egyptians were building the pyramids, demonstrating the remarkable resilience of these Ice Age survivors. The American mastodon was a shorter, stoutly built proboscidean that browsed on trees and shrubs in woodland habitats. Unlike mammoths, mastodons were primarily browsers that used their straighter tusks and different tooth structure to process woody vegetation. They occupied the forest edges and woodlands that bordered the great grasslands, creating a complementary relationship with their mammoth relatives. But elephants weren't the only mammals, reaching gigantic proportions during the Pleistocene. Today, sloths are molasses-moving tree dwellers, roughly the size of a dog. But in Ice Age North America, sloths were an entirely different beast. The giant ground sloths of the late Pleistocene were bear-sized herbivores that stood 12 feet on their hind legs and weighed up to 3,000 pounds. The giant ground sloth, Megatherium, was an herbivore that could stand over 12 feet tall and weigh up to 4 tons. It used its size and claws to pull down tree branches for feeding. This giant stood 7 meters tall and weighed 7 tons. Megatherium, giant beast in Latin, lived from about 35 million to 11,000 years ago, coinciding with the last Ice Age. These were not the slow-moving creatures we might imagine. Giant ground sloths were surprisingly agile and could rear up on their hind legs to browse vegetation that no other mammal could reach. One giant sloth species, the Jefferson ground sloth, Megalonyx jeffersoni, was named for Thomas Jefferson, who initially believed that sloth fossils were a type of colossal cat that he dubbed the Megalonyx, giant claw. Meb. Jeffersoni was apparently the most wide-ranging giant ground sloth. Fossils are known from many Pleistocene sites in the United States, including most of the states east of the Rocky Mountains, as well as along the West Coast. It was the only ground sloth to range as far north as the present-day Yukon and Alaska. Diversity of Ice Age herbivores extended far beyond the famous mammoths and sloths. Beavers the size of bears engineered waterways across North America. The giant beaver, Castoroides ohioensis, grew to the size of a black bear, weighing up to 220 pounds. Unlike modern beavers, these giants may not have built dams, instead using their massive size and powerful claws to modify aquatic environments in ways we can barely imagine. The ancient bison. Bison antiquus lived from about 240,000 to 10,000 years ago and was significantly larger than modern bison. Standing 6 feet at the shoulder and weighing over a ton, with horn spans reaching 6 feet, these giants dominated the grasslands of Pleistocene North America. Their herds may have numbered in the millions, creating one of the most spectacular wildlife displays in Earth's history. Even larger was Bison latifrons, which reached a weight from 1,250 kilograms, 2,760 pounds, to 2,000 kilograms, 4,400 pounds, 4.75 meters, 15.6 feet in length, shoulder height of 2.31 meters, 7.6 feet, and had horns that spanned 2.13 meters, 7 feet 0 in. This was a bison built on a scale that defies modern comprehension. With horns wider than most modern cars dot the carnivores that hunted. These giants were equally impressive. Predators included the saber-toothed cat, Smilodon fatalis, a robust hunter about the size of a lion, weighing up to 620 pounds. It used its 8-inch-long canine teeth to deliver fatal bites to large prey. Smilodon was perfectly adapted for hunting the megafauna of its time, with powerful forelimbs for grappling prey and the most sophisticated killing apparatus ever evolved by a mammalian predator. Another predator was the direwolf, EOCENE dirus. Similar in size to large gray wolves, but with a heavier build and a more powerful bite. Fossil evidence suggests they hunted in packs, tackling herbivores like horses and bison. Dire wolves were more robust than modern wolves, with larger heads, more powerful jaw muscles, and teeth designed for crushing bone. They represented the ultimate pack-hunting carnivore, capable of bringing down prey many times, their own size through coordinated group attacks. The giant short-faced bear, Arctodus simus, was the largest mammalian land carnivore of its time, standing over 11 feet tall on its hind legs and built for long-distance travel across open grasslands. The short-faced bear was huge and had much longer legs than modern bears relative to the body, which has given rise to the idea that it was a cursorial predator, meaning that it ran after prey. This massive bear could have weighed up to 957 kg, 2,110 pounds, making it larger than any modern land carnivore. South America developed its own spectacular megafauna during the Pleistocene. In the Pampas, Megatherium americanum lived alongside other megafauna species, including the large ground sloth, Lestodon, along with the smaller, but still large, ground sloths, Mylodon, Glossotherium and Solidotherium, the glyptodonts, vary. Large armadillos with fused round carapaces covering the body. Glyptodon, Dodicurus and Pacthus, the large camel-like ungulate Macrauchenia and rhinoceros-like. Toxodon. Glyptodonts were perhaps the most bizarre of all Pleistocene mammals. These giant armadillos grew to the size of small cars, with domed shells that could reach 5 feet in height. Some species, like Dodicurus, weighed over a ton and possessed spiked tail clubs that functioned like medieval maces. These were living tanks that dominated South American grasslands for millions of years. The toxodonts represented South America's answer to hippos and rhinos. Toxodon platensis was a massive, barrel-shaped herbivore that weighed over a ton and possessed continuously growing teeth capable of processing the toughest vegetation. Charles Darwin himself discovered Toxodon fossils during the voyage of the Beagle and was amazed by their bizarre anatomy. Australia developed its own unique megafauna, including the giant wombat-like Diprotodon, which weighed up to 3 tons and was the largest marsupial ever to evolve. The giant Goanna megalania was a monitor lizard that grew to 23 feet in length and may have weighed over a ton, making it one of the largest terrestrial carnivores of the Pleistocene. The diversity of Pleistocene megafauna extended to every continent except Antarctica. Europe had woolly rhinoceroses, cave bears that dwarfed modern grizzlies, and giant deer with antler spans reaching 12 feet. Africa retained most of its megafauna, but still lost impressive giants like Pelorivus, a buffalo with horns spanning over 6 feet. These magnificent creatures created ecosystems unlike anything in the modern world. The biomass supported by Pleistocene landscapes was extraordinary. Estimates suggest that the mammoth steppe supported 10 times more large mammal biomass per square kilometer than modern African savannas. This was a world where giants were the norm rather than the exception. The megafauna shaped their environments as profoundly as their environments shaped them. Mammoth herds created and maintained the grassland ecosystems they depended upon, trampling shrubs and fertilizing the soil with their dung. Giant ground sloths dispersed seeds across entire continents, while massive beavers engineered wetland systems that supported countless other species. The behavioral complexity of these giants matched their physical impressions. Mammoth societies were matriarchal, led by experienced older females who knew migration routes and seasonal feeding areas passed down through generations. Their communication systems included infrasonic calls that could travel for miles, allowing herds to coordinate movements across vast landscapes. Cave paintings and early human artifacts provide glimpses of how these magnificent creatures interacted with early human populations. The relationship was complex, sometimes predator and prey, sometimes competitors for resources, always filled with mutual respect and fear. Humans honored the megafauna in their art, suggesting deep spiritual connections to these giants that dominated their world. Yet even as these magnificent creatures reached their evolutionary peak, forces were gathering that would bring about their doom. The Pleistocene world of giants was about to face its greatest challenge, as climate change and the arrival of a new and unprecedented threat would test their ability to survive. The age of mammalian giants was approaching its end, and with it would come one of the most devastating extinction events in Earth's history. Chapter 7. The Great Dying, the End of the Pleistocene. Approximately 11,700 years ago marked one of the most catastrophic extinction events in Earth's history. In a geological instant just a few thousand years, the magnificent giants that had dominated terrestrial ecosystems for millions of years vanished from the face of the Earth. The late Pleistocene to the beginning of the Holocene saw the extinction of the majority of the world's megafauna, typically defined as animal species having body masses over 44 kilograms, 97 pounds, which resulted in a collapse in faunal density and diversity across the globe. This wasn't just another extinction event. It was a selective catastrophe that targeted the largest and most magnificent creatures our planet had ever produced. Overall, during the late Pleistocene, about 65% of all megafaunal species worldwide became extinct, rising to 72% in North America, 83% in South America, and 88% in Australia, with all mammals over 1,000 kilograms, 2,200 pounds, becoming extinct in Australia and the Americas, and around 80% globally. The numbers tell a story of devastation that defies comprehension. The extinction pattern was unprecedented in its selectivity. The extinctions during the late Pleistocene are differentiated from previous extinctions by their extreme size bias towards large animals, with small animals being largely unaffected, and widespread absence of ecological succession to replace these extinct megafaunal species. Small mammals, birds, reptiles, and amphibians largely survived while their giant relatives perished. This size-selective extinction created empty landscapes where ecological niches that had been filled for millions of years suddenly stood vacant. The timing of these extinctions varied dramatically across the globe, providing crucial clues about their causes. Extinctions in northern Eurasia were staggered over tens of thousands of years, between 50,000 and 10,000 years ago, while extinctions in the Americas were virtually simultaneous, spanning only 3,000 years at most. In North America, where 32 genera of large mammals vanished during an interval of about 2,000 years, centered on 11,000 BP, the extinction event is most distinct. The correlation between human arrival and megafaunal extinction is striking and sobering. The proportion of megafauna extinctions is progressively larger the further the human migratory distance from Africa, with the highest extinction rates in Australia and North and South America. The increased extent of extinction mirrors the migration pattern of modern humans. The further away from Africa, the more recently humans inhabited the area, the less time those environments, including its megafauna, had to become accustomed to. Humans and vice versa. Evidence supporting the prehistoric overkill hypothesis includes the persistence of megafauna on some islands for millennia, past the disappearance of their continental cousins. Ground sloths survived on the Antilles long after North and South American ground sloths were extinct. Woolly mammoths died out on remote Wrangel Island 6,000 years after their extinction on the mainland, and Steller's sea cows persisted off the isolated and uninhabited Commander Islands for thousands of years after they had vanished from the continental shores of the North Pacific. The later disappearance of these island species correlates with the later colonization of these islands by humans. The overkill hypothesis, while compelling, faces significant challenges from the archaeological record. There is little evidence of human interaction with extinct Australian megafauna, with one notable exception being the burning of Genornis, a type of giant dromornithid bird related to ducks' eggshells. The scarcity of kill sites and the apparent coexistence of humans and megafauna for thousands of years in some regions suggest that the relationship between human expansion and megafaunal extinction was complex. Direct evidence of human hunting of megafauna, while rare, is nonetheless significant. There is evidence for the butchery of Megatherium by humans. 2 M. americanum bones, an ulna, and an atlas vertebra from separate collections bear cut marks suggestive of butchery, with the latter suggested to represent an attempt to exploit the contents of the head. A kill site dating to around 12,600 years before present BP is known from Campo Laborde in the Pampas in Argentina, where a single individual of M. americanum was slaughtered and butchered at the edge of a swamp, which is the only confirmed giant ground sloth kill site in the Americas. At the Paso Otero 5 site in the Pampas of northeast Argentina, fishtail points are associated with burned bones of Megatherium americanum and other extinct megafauna. The bones appear to have been deliberately burned as a source of fuel. While direct evidence of hunting remains limited, the archaeological record suggests that humans were certainly capable of killing the largest mammals of their time when the opportunity arose. Climate change represents the other major hypothesis for explaining the late Pleistocene extinctions. Abrupt climatic change also occurred at the time of the megafaunal extinctions, and so timing alone does not clearly differentiate one hypothesis from the other. The climatic change hypothesis takes a number of forms, but essentially focuses on the reorganization of vegetation, on the availability of food, including nutrient value, and on the general environmental disruption and stress that resulted as climates became more seasonal. the end of the last glacial period brought dramatic environmental changes that fundamentally altered the ecosystems that had supported megafauna for hundreds of thousands of years. As the last glacial period ended, rising global temperatures melted the ice sheets. This warming altered landscapes, causing the mammoth steppe to be replaced by forests and wetlands. This shift removed the primary food sources for large grazers and disrupted the ecosystems the megafauna depended on. The mammoth steppe, that vast productive grassland that had stretched across northern continents, was perhaps the greatest casualty of post-glacial climate change. This ecosystem had supported the highest density of large mammals in Earth's history, but it could not survive the warming temperatures and changing precipitation patterns of the Holocene. As permafrost melted and forests expanded, the grasses and herbs that had fed countless generations of megafauna disappeared in temperate Eurasia and North America. Megafauna extinction concluded simultaneously with the replacement of the vast periglacial tundra by an immense area of forest. Glacial species, such as mammoths and woolly rhinoceros, were replaced by animals better adapted to forests, such as elk, deer, and pigs. Reindeers, caribou, retreated north, while horses moved south to the Central Asian steppe. This transformation happened about 10,000 years ago, despite the fact that humans colonized North America less than 15,000 years ago, and non-tropical Eurasia nearly 1 million years ago. The speed of these environmental changes may have been too rapid for large mammals to adapt. Being big comes with big challenges. For example, gigantic mammals needed huge amounts of food to survive. They could not produce many offspring because they needed many years to become adults and capable of reproduction, and the gestation period was quite long. These difficulties made large mammals more vulnerable to changes in their habitats declining populations because they would need long periods of time and a lot of resources to maintain or recover their numbers. The Younger Dryas period, a sudden return to glacial conditions that lasted from about 12,900 to 11,700 years ago, may have delivered the final blow to many megafaunal populations. This abrupt climatic reversal lasted over 1,000 years and brought severe cold and drought to much of the northern hemisphere. For megafauna already stressed by habitat changes and possibly human hunting pressure, the Younger Dryas may have pushed many species beyond their ability to recover. Some researchers have proposed that disease played a role in the megafaunal extinctions. The hyperdisease hypothesis suggests that pathogens carried by humans, their domestic animals, or commensal species like dogs may have devastated naive megafaunal populations with no evolved resistance. However, direct evidence for disease-driven extinctions remains limited, and the hypothesis struggles to explain the selectivity of the extinctions for large mammals. Extraterrestrial impact has also been proposed as a cause of the late Pleistocene extinctions. The Younger Dryas impact hypothesis suggests that a cosmic impact or airburst event triggered the Younger Dryas period and contributed to megafaunal extinctions. However, this hypothesis remains controversial, with limited geological evidence for a major impact event at the appropriate time. The reality is likely that multiple factors combined to create a perfect storm of extinction pressures. It appears likely that the causes of extinction varied in different geographic areas under different conditions, and that both climatic change and human activities played roles, but of varying importance in different situations. The synergistic effects of climate change, human hunting, habitat fragmentation, and possibly disease-created conditions that even the most successful mammalian lineages could not overcome. The extinction of specific lineages tells individual stories of loss that collectively paint a picture of global catastrophe. The mighty woolly mammoth, which had survived multiple glacial cycles and thrived in the harshest environments on Earth, finally succumbed around 10,000 years ago on the mainland. The youngest unambiguous dates for Megatherium are from the end of the late Pleistocene. Supposed early Holocene dates obtained for Megatherium americanum and other pampas megafauna have been questioned, with suggestions that they are likely due to humic acid contamination of the collagen used to radiocarbon date the bones. Saber-toothed cats, the ultimate mammalian predators, vanished along with their prey. Smilodon became extinct around 12,000 years ago as part of the end Pleistocene extinction event, simultaneously with the majority of other large mammals in the Americas. The disappearance of these apex predators left ecological niches that have never been completely filled by surviving species. Giant ground sloths, which had successfully colonized both North and South America and thrived for millions of years, could not adapt to the rapidly changing post-glacial world. Megatherium disappeared simultaneously along with the vast majority, 80%, of other large megafaunal South American mammals, as part of the end Pleistocene extinction event. Their extinction removes some of the most important seed dispersers in New World ecosystems, with consequences that persist to this day. The great short-faced bears, both North and South American species, vanished along with their prey base. The Rontothers had already been extinct for millions of years, but their ecological role as browsers of coarse vegetation was filled by various megafaunal species that now also disappeared. The giant beavers that had engineered waterways across North America left behind empty dams that gradually deteriorated without maintenance. European megafauna suffered their own losses, though less severe than those experienced in the Americas and Australia. Cave bears, which had survived multiple glacial cycles in their mountain refugia, finally succumbed to the combination of climate change and human competition for cave sites. Woolly rhinoceroses disappeared from their steppe habitats as forests replaced the grasslands they depended upon. Australia's losses were perhaps the most severe in relative terms. Studies from the late 2010s onward suggested that many megafauna species survived later than previously assumed by some authors and were contemporaneous with humans in Australia, though some studies still argue that climate change was the primary cause of their extinction. The giant kangaroos, massive wombats, and predatory monitor lizards that had dominated Australian landscapes for millions of years vanished, leaving behind ecosystems dominated by much smaller species. The ecological consequences of the late Pleistocene extinctions extended far beyond the disappearance of individual species. Recent studies have indicated that the extinction of megafaunal herbivores may have caused a reduction in atmospheric methane. One study examined the change in the methane concentration in the atmosphere at the end of the Pleistocene epoch after the extinction of megafauna in the Americas. After early humans migrated to the Americas about 13,000 BP, their hunting and other associated ecological impacts led to the extinction of many megafaunal species there. Calculations suggest that this extinction decreased methane production by about 9.6 million tons per year. The loss of megafaunal seed dispersers fundamentally altered plant communities across continents. Many large-seeded plants that had co-evolved with giant mammals found themselves without effective dispersal mechanisms, leading to population declines and local extinctions that continue today. The ghost of evolution, anachronistic fruits, like avocados that evolved to be dispersed by giant ground sloths, persist as reminders of the ecological partnerships that were severed by the extinctions. Predator-prey relationships that had been refined over millions of years collapsed overnight. The disappearance of megafaunal herbivores left predator communities unsupported, while the loss of top predators allowed surviving herbivore populations to expand in ways that often led to overgrazing and habitat degradation. These cascading effects reshaped entire ecosystems and continue to influence ecological dynamics today. The late Pleistocene extinctions marked the end of an era that had lasted for over 60 million years. Since the extinction of the dinosaurs, mammals had evolved into increasingly spectacular forms, reaching sizes and developing specializations that pushed the boundaries of what was biologically possible. The giants of the Ice Age represented the ultimate expression of mammalian evolution, and their loss impoverished the world in ways that are still being discovered and understood. The empty landscapes left behind by the extinct megafauna serve as silent testimony to one of the greatest catastrophes in natural history. Where once thunderous herds of mammoths crossed Arctic plains, where giant ground sloths shaped entire ecosystems, where saber-toothed cats stalked prey larger than any modern animal, now only smaller mammals remain, survivors in a world suddenly too large for its inhabitants. This great dying was not just an extinction event. It was the end of the age of mammalian giants, the close of a chapter in Earth's history that will never be repeated. The forces that drove these extinctions continue to operate today as human populations expand and climate change accelerates, raising disturbing questions about the fate of the remaining large mammals that survived the Pleistocene bottleneck. Chapter 8: Survivors in a Diminished World, the Holocene Epoch, beginning 11,700 years ago and continuing to the present day, opened on a world dramatically impoverished by the late Pleistocene extinctions. The giants were gone. The ecological networks that had sustained them were broken, and the survivors faced the challenge of rebuilding mammalian communities from the fragments that remained. This new world was smaller, quieter, and less diverse than anything mammals had experienced since the aftermath of the dinosaur extinction 66 million years ago. The mammals that survived the Great Dying were not a random sample of Pleistocene diversity. They were the lucky few whose particular combinations of size, ecological requirements, reproductive strategies, and behavioral flexibility allowed them to navigate the multiple pressures of climate change, human expansion, and ecosystem collapse. Understanding why these species survived while their giant relatives perished provides crucial insights into the nature of extinction and the requirements for long-term survival in a human-dominated world. Size was perhaps the most important factor determining survival. Africa, South Asia, and Southeast Asia experienced more moderate extinctions than other regions, retaining their largest mammals including elephants, rhinoceroses, hippopotamuses, giraffes, and various large antelopes. These regions had been coevolving with human ancestors for millions of years, allowing their megafauna to gradually adapt to human presence rather than facing the sudden shock experienced by naive faunas in other continents. African elephants represent the most successful large mammal survivors, though even they are mere shadows of Pleistocene diversity. Where once dozens of proboscidean species roamed every continent except Antarctica and Australia, today only 3 elephant species survive: African bush elephants, African forest elephants, and Asian elephants carry the genetic legacy of a lineage that once included straight-tusked elephants larger than any modern species. Mammoth species adapted to every climate from tropical to Arctic, and bizarre specialized forms like the shovel-tusked mastodons. These surviving elephants demonstrate the behavioral complexity that may have been key to their persistence. Their matriarchal societies, with their accumulated knowledge of seasonal resources, migration routes, and responses to environmental challenges, provided a cultural buffer against rapid environmental change. The ability to modify behavior within a single generation, rather than relying solely on genetic adaptation over multiple generations, proved crucial for surviving the unpredictable conditions of the Pleistocene-Holocene transition. Rhinoceroses tell a similar story of survival and decline. 5 species survive today from a lineage that once included dozens of species, including giants like Elasmotherium, the Siberian unicorn with its massive single horn, and Coryphodon, one of the earliest large mammalian herbivores. Modern rhinoceroses occupy only a fraction of their historical range and exist in populations so reduced that their long-term survival remains uncertain despite intensive conservation efforts. The great cats represent another group of large mammal survivors, though their story is one of profound loss masked by the success of a few adaptable species. Lions once roamed across Europe, Asia, Africa, and the Americas in a diversity of subspecies adapted to different environments. Today, they survive only in fragmented populations in Africa and a tiny relict population in India's Gir forest. Tigers, leopards, jaguars, and pumas persist across reduced ranges, serving as the diminished heirs to a golden age of large predators. The absence of saber-toothed cats from the modern world represents one of the most significant gaps in current mammalian diversity. For over 20 million years, Machaerodontine cats were among the most successful large predators on Earth, evolving multiple times and colonizing every continent except Antarctica and Australia. Their extinction left ecological niches that have never been fully filled, fundamentally altering predator-prey dynamics across the globe. Medium-sized mammals fared better than their giant relatives, though many still suffered significant range reductions and population declines. Bears survived on every continent where they existed during the Pleistocene, but the diversity of bear species was drastically reduced. The giant short-faced bears of both North and South America vanished, leaving behind only the more omnivorous and behaviorally flexible species we know today. Wolves represent one of the most successful large predator survivors, though even their story is one of dramatic range reduction. Gray wolves once inhabited the entire northern hemisphere, from Arctic tundra to desert margins, in dozens of subspecies adapted to local conditions. Today, they survive in fragmented populations that represent a tiny fraction of their historical range, though their behavioral flexibility and pack hunting strategies have allowed them to persist where solitary predators have failed. The evolutionary trajectory of dogs from wolves represents one of the most remarkable examples of mammalian adaptation to human-dominated environments. The domestication of dogs began during the late Pleistocene or early Holocene, creating the first mutualistic relationship between humans and large mammals. This partnership not only ensured the survival of the wolf lineage, but transformed it into one of the most successful large mammals on Earth, with domestic dogs now outnumbering wolves by several orders of magnitude. Ungulates show a complex pattern of survival and extinction that illuminates the factors that determined Holocene success. Wild horses vanish from the Americas where they had evolved, surviving only in small populations in Central Asia before being reintroduced by Europeans thousands of years later. Yet their domestic descendants became one of the most successful large mammals in human history, illustrating how partnership with humans could ensure survival where wild populations failed. Bison in North America survived the Pleistocene extinctions, only to face near extinction during the 19th century from human hunting and habitat destruction. Their recovery from fewer than 1,000 individuals to current populations of several hundred thousand demonstrates the resilience that allowed some mammalian lineages to survive multiple crises. However, modern bison represent only a tiny fraction of the diversity that once existed, with several species and countless regional populations lost forever. Deer and their relatives showed remarkable success in adapting to post-extinction ecosystems. White-tailed deer, roe deer, red deer, and numerous other cervid species not only survived but often thrived in human-modified landscapes. Their behavioral flexibility, broad dietary tolerance, and rapid reproductive rates proved well suited to the fragmented and rapidly changing habitats of the Holocene world. The success of small mammals during the Holocene transition illustrates the advantages of modest size and behavioral flexibility in unstable environments. Rodents underwent spectacular diversification in post-extinction ecosystems, rapidly filling niches left vacant by extinct megafauna. Rats, mice, squirrels, and their relatives colonized human-modified environments with unprecedented success, becoming some of the most abundant mammals on Earth. Bats, the only flying mammals, showed remarkable resilience during the extinctions. Their ability to exploit three-dimensional habitat space, migrate long distances, and adapt to diverse food sources allowed them to maintain much of their Pleistocene diversity. Today, bats represent nearly a quarter of all mammal species, demonstrating the advantages of morphological innovation in surviving environmental crises. Marine mammals tell a different story, having largely escaped the terrestrial extinctions while facing their own unique challenges. Whales, dolphins, seals, and their relatives maintain much of their diversity through the Pleistocene-Holocene transition, though some species like Steller sea cow succumbed to human hunting in historical times. The ocean provided a buffer against the rapid environmental changes that devastated terrestrial ecosystems. The behavioral and ecological changes that occurred in survivor communities reveal the profound impacts of losing the megafauna. Without large herbivores to maintain grasslands through grazing and trampling, many open habitats began reverting to forest. This habitat change favored forest-adapted species while disadvantaging those adapted to open environments, creating a cascade of secondary extinctions and range contractions that continued for millennia after the initial megafaunal collapse. Predator communities were fundamentally restructured by the loss of both large prey and large competitors. Medium-sized predators like wolves and large cats suddenly found themselves as the apex predators in ecosystems that had previously been dominated by much larger species. This ecological release allowed some species to expand their ranges and diversify their prey base, but it also left many ecological functions unfulfilled. The loss of large-bodied seed dispersers had cascading effects on plant communities that persist today. Many tree species, particularly those with large seeds that evolved to be dispersed by megafauna, suffered range contractions and population declines. Some, like the American chestnut, remained abundant for thousands of years before succumbing to other factors, while others began slow declines that continue today. Island ecosystems provide natural experiments in mammalian survival and extinction. Many islands retained their megafauna long after continental extinctions, with giant ground sloths surviving in the Caribbean until just a few thousand years ago, and dwarf mammoths persisting on California's Channel Islands until about 13,000 years ago. These delayed extinctions closely correlate with human arrival on these islands, providing some of the strongest evidence for human causation of megafaunal extinctions. The pattern of Holocene mammalian diversity is dramatically different from that of any previous geological epoch. Instead of being dominated by large-bodied specialists adapted to stable climatic conditions, modern mammalian communities are characterized by smaller, more behaviorally flexible generalists capable of rapid adaptation to changing conditions. This represents a fundamental shift in mammalian evolution, from optimization for stable environments to optimization for environmental unpredictability. Human commensal species that benefit from association with humans without being fully domesticated represent a new category of mammalian success. Brown rats, house mice, and various other species have achieved global distributions and population sizes that rival or exceed those of any wild mammal species. Their success illustrates the opportunities available to mammals capable of exploiting human-modified environments. The domestication of mammals represents humanity's most direct intervention in mammalian evolution. Cattle, sheep, goats, pigs, horses, and dogs have achieved population sizes and geographic distributions that far exceed those of their wild ancestors. These domestic animals now constitute a significant portion of all large mammal biomass on Earth, fundamentally altering the balance of mammalian communities worldwide. Conservation efforts during the modern era have prevented numerous additional extinctions and enabled the recovery of some species from critically low populations. American bison, gray wolves, brown bears, and numerous other species exist today only because of active human intervention to prevent their extinction. This marks a new phase in the relationship between humans and large mammals, from exploitation towards stewardship. The modern distribution of mammalian diversity reflects the combined impacts of natural climate change, human expansion, and ecological disruption over the past 12,000 years. Tropical regions, which experienced less severe climate change and later human colonization, retain more of their original mammalian diversity than temperate and Arctic regions. However, even these refugia are now experiencing rapid habitat loss and fragmentation as human populations expand. The Anthropocene epoch, our current geological age, presents new challenges for mammalian survival that echo those faced during the late Pleistocene extinctions. Rapid climate change, habitat fragmentation, pollution, and direct exploitation threaten many of the species that successfully navigated the previous extinction crisis. The survivors of the Great Dying now face the possibility of a second wave of extinctions that could further impoverish mammalian communities worldwide. Yet the story of Holocene mammals is not entirely one of loss and decline. Some species have shown remarkable adaptability to human-dominated landscapes, expanding their ranges and populations in response to new opportunities. Urban mammals, from raccoons and coyotes in North America to macaques and leopards in Asia, demonstrate the continuing potential for mammalian evolution and adaptation even in heavily modified environments. The mammals of today carry within their DNA the genetic legacy of 66 million years of mammalian evolution. They are the inheritors of innovations developed by countless extinct lineages, from the basic mammalian body plan established in the Triassic to the sophisticated behavioral adaptations refined during the Cenozoic. Their survival represents not just individual species success, but the continuation of evolutionary experiments that began when the first mammals emerged from the shadow of the dinosaurs. Understanding the factors that allowed these species to survive while their giant relatives perished provides crucial guidance for conservation efforts in our current extinction crisis. The mammals of the Holocene world demonstrate that survival in times of rapid environmental change requires behavioral flexibility, reproductive resilience, and the ability to exploit new ecological opportunities as they arise. These lessons from the survivors may be essential for navigating the challenges that lie ahead in our increasingly human-dominated world. Chapter 9. Masters of the Skies and Seas while terrestrial. Mammals were conducting their spectacular experiments with size and form. Two other mammalian groups were writing equally remarkable chapters in the story of vertebrate evolution. The conquest of the air by bats and the return to the sea by whales represent two of the most dramatic evolutionary transformations in natural history. These mammals didn't just adapt to new environments, they revolutionized them, developing capabilities that rival and often surpass those of animals that had evolved in these realms for hundreds of millions of years. The evolution of flight in mammals represents one of nature's most impressive engineering achievements. Bats are the only mammals to achieve true powered flight, and their success in aerial environments has been nothing short of spectacular. Today, bats represent nearly a quarter of all mammal species, making them one of the most diverse mammalian orders. Their evolutionary radiation has produced forms adapted to every conceivable aerial niche, from tiny bumblebee bats weighing less than a penny to flying foxes with 6-foot wingspans. The fossil record of early bats remains frustratingly incomplete, but what evidence exists suggests that the transition from terrestrial to aerial life happened with remarkable speed. The earliest known bat fossil, Onychonycteris from the Eocene epoch, already possessed fully developed wings and the basic body plan that characterizes modern bats. This suggests that the crucial evolutionary steps in bat origins occurred rapidly. During the Paleocene, when fossil preservation conditions were poor for small, delicate mammalian skeletons, the wing structure of bats represents a fundamentally different solution to the challenge of powered flight than that evolved by birds. Where bird wings are supported by modified arm bones and feathers, bat wings consist of thin membranes stretched between extremely elongated finger bones. This membrane wing design provides extraordinary maneuverability and the ability to make rapid adjustments to wing shape during flight. Bats can execute aerial maneuvers that would be impossible for birds of similar size, including hovering, backwards flight, and instantaneous direction changes. The diversity of bat feeding strategies demonstrates the evolutionary potential unleashed by the conquest of the air. Most people think of bats as insectivores, and indeed the majority of bat species feed on flying insects captured through sophisticated echolocation hunting. But the radiation of bats has produced specialists adapted to virtually every conceivable food source. Fruit bats have evolved acute vision and specialized digestive systems for processing plant materials. Nectar-feeding bats have developed elongated tongues and hovering flight capabilities that rival those of hummingbirds. Fish-eating bats use echolocation to detect fish moving beneath water surfaces, then swoop down to capture prey with specialized claws. Perhaps most remarkable are the vampire bats, which have evolved to feed exclusively on blood. These highly specialized predators possess heat-sensing organs that allow them to locate blood vessels beneath their victim's skin, along with razor-sharp teeth for making precise incisions and anticoagulant saliva that keeps blood flowing. Their social behaviors include food sharing among colony members, representing one of the few examples of reciprocal altruism documented in non-human mammals. The echolocation systems developed by bats represent sensory capabilities that exceed anything achieved by human technology until the mid-20th century. The bats can navigate in complete darkness, track multiple moving targets simultaneously, and distinguish between objects that differ in size by just a few millimeters. Their biocene systems are so sophisticated that they can see the internal structure of objects, detect wires as thin as human hair, and hunt successfully in environments cluttered with obstacles that would challenge even modern radar systems. Different bat species have evolved echolocation calls adapted to their specific hunting strategies and environments. Open-air hunters use long-range, high-intensity calls that can detect prey at distances of over 100 feet. Forest bats employ frequency-modulated calls that provide detailed information about nearby objects, but sacrifice detection range for precision. Some species have even evolved stealth echolocation systems with calls, so quiet they can approach prey without being detected by insects that have evolved ears specifically to avoid bat predation. While bats were mastering the skies, another group of mammals was undertaking an equally dramatic evolutionary journey back to the sea. The evolution of whales from terrestrial ancestors represents one of the most complete and well-documented major evolutionary transitions in the fossil record. This transformation involved not just changes in body shape and size, but fundamental reorganization of physiology, behavior, and sensory systems to meet the challenges of fully aquatic life. The story of whale evolution begins in the Eocene epoch, with creatures like Pachycetus, a wolf-sized mammal that lived along the shores of ancient Pakistan. Pachycetus was clearly terrestrial, with 4 functional legs and ears adapted for hearing in air. Yet its skull structure and tooth morphology show clear relationships to later whales, marking it as one of the earliest members of the whale lineage. The transition from Pachycetus to fully aquatic whales involved a series of intermediate forms that document each major step in this evolutionary transformation. Ambulocetus, the walking whale, represents a crucial intermediate stage in whale evolution. This 4-meter-long predator retained 4 functional limbs, but it developed a body plan clearly adapted for aquatic locomotion. Its legs were positioned to provide thrust during swimming, while its elongated skull and teeth were specialized for capturing fish and other aquatic prey. Ambulocetus could move on land when necessary, but was primarily an aquatic hunter that spent most of its time in coastal waters. The next stage in whale evolution is represented by Basilosaurus, a serpentine whale that reached lengths of over 50 feet. Basilosaurus had tiny vestigial hind limbs that played no role in locomotion, marking the final abandonment of terrestrial mobility. Its body was perfectly streamlined for aquatic life, with powerful tail flukes for propulsion and forelimbs, modified into steering flippers. The transformation was nearly complete. Mammals had successfully invaded the marine realm and were beginning to compete with sharks and other marine predators that had ruled the oceans for hundreds of millions of years. The physiological challenges overcome during whale evolution were immense. Terrestrial mammals must deal with the problems of breathing air while spending extended periods underwater, maintaining body temperature in a medium that conducts heat away from the body 25 times faster than air, and functioning at depths where pressure can crush air-filled organs. Whales evolved solutions to all these challenges and more, developing capabilities that allow them to thrive in environments that would be instantly fatal to their terrestrial relatives. The diving abilities of modern whales represent some of the most extreme physiological adaptations ever evolved by mammals. Sperm whales can dive to depths exceeding 7,000 feet and remain submerged for over 2 hours. These abilities require sophisticated adaptations, including collapsible lungs that prevent nitrogen narcosis, oxygen-storing proteins in muscles and blood that allow extended underwater activity, and pressure-resistant organs that can function at depths where the pressure exceeds 200 times that at sea level. The sensory adaptations of whales rival those of bats in their sophistication. Toothed whales evolved echolocation systems independently, from bats developing biocentric capabilities that allow them to navigate and hunt in the dark depths of the ocean. Whale echolocation is even more powerful than that of bats, with some species capable of detecting objects buried in sediment or distinguishing between materials of different density inside opaque objects. Baleen whales took a different evolutionary path, developing filter-feeding systems that allow them to harvest vast quantities of small prey from ocean waters. The baleen plates that give these whales their name are made of keratin, the same material as hair and fingernails, and function as biological sieves that constrain millions of small crustaceans and fish from each mouthful of seawater. This feeding strategy has allowed baleen whales to grow to enormous sizes, with blue whales reaching lengths of over 100 feet and weights exceeding 200 tons, making them the largest animals ever to exist on Earth. The social behaviors of whales demonstrate intelligence and complexity that rivals that of terrestrial mammals. Many whale species live in complex social groups with sophisticated communication systems. Humpback whales compose and perform songs that can last for hours and be heard across entire ocean basins. These songs change over time in ways that suggest cultural transmission of information within whale populations. Sperm whales live in matrilineal groups led by experienced older females, similar to elephant societies, and use distinctive patterns of echolocation clicks that may function as family dialects. The migration patterns of whales represent some of the longest journeys undertaken by any mammal. Gray whales travel over 12,000 miles annually between feeding areas in the Arctic and breeding grounds in Mexico. Humpback whales make similarly epic journeys, with some populations traveling from polar feeding areas to tropical breeding grounds and back again each year. These migrations require navigation abilities that remain poorly understood, but may involve magnetic field detection, celestial navigation, and memorization of underwater topographic features. The evolution of gigantism in whales followed different patterns than terrestrial mammalian gigantism, where large land mammals were constrained by the mechanical properties of bone and the challenges of supporting massive bodies against gravity. Marine mammals faced different physical limitations. The buoyancy provided by seawater allowed whales to evolve body sizes that would be mechanically impossible on land, but they faced other constraints related to heat conservation, oxygen storage, and the energetics of moving massive bodies through water. The success of both bats and whales demonstrates that mammalian evolutionary potential extends far beyond terrestrial environments. These groups didn't just colonize new habitats, they revolutionized them, becoming dominant players in aerial and marine ecosystems respectively. Their evolutionary innovations continue to inspire human technology, from sonar systems based on whale echolocation to aircraft designs influenced by bat wing mechanics. The diversity achieved by flying and swimming mammals rivals that of their terrestrial relatives. Bats have evolved into over 1,400 species, occupying every conceivable aerial niche, while whales and dolphins have diversified into nearly 90 species that dominate marine ecosystems from polar seas to tropical waters. Together, these groups demonstrate that the evolutionary creativity that produced the terrestrial giants was not limited to land-based environments. Today, both bats and marine mammals face challenges similar to those confronting terrestrial wildlife. Climate change is altering the ecosystems they depend upon, while human activities create new threats from pollution, habitat destruction, and direct persecution. Wind turbines pose novel hazards to bat populations, while ship strikes and fishing gear entanglement threaten whale populations worldwide. The conservation of these remarkable mammals requires understanding not just their biology, but the complex three-dimensional environments they inhabit and the global-scale migrations that define their lives. The evolutionary success of bats and whales provides hope for mammalian adaptability in our changing world. These groups demonstrate that mammals are capable of radical evolutionary transformations when faced with new opportunities or challenges. Their conquest of air and sea shows that mammalian evolution is far from exhausted, and that future evolutionary innovations may be as remarkable as anything produced during the golden age of terrestrial giants. Chapter 10. The Human Factor. No story of mammalian evolution would be complete without examining the rise of the most influential mammal species in Earth's history. The evolution of humans and their subsequent impact on global ecosystems represents a fundamentally new chapter in the mammalian story, one that has transformed the rules of evolution itself and created challenges that no previous mammalian species has ever faced. Understanding this transformation is crucial for comprehending both the current state of mammalian diversity and the future prospects for mammalian evolution in an increasingly human-dominated world. The human lineage emerged from the broader primate radiation that began during the Paleocene and Eocene epochs. Early primates were small, tree-dwelling mammals that developed enhanced vision, grasping hands, and enlarged brains to navigate complex arboreal environments. The first primates appeared in Africa, though the mystery of their early evolution continues to puzzle paleontologists. For millions of years, primates remained relatively small and ecologically marginal members of mammalian communities, overshadowed by the giant ungulates and carnivores that dominated terrestrial ecosystems. The divergence of the human lineage from other great apes occurred approximately 6 to 7 million years ago in Africa, during a period of significant climate change that was fragmenting the continent's forests and expanding grassland habitats. This environmental transformation created new evolutionary pressures that would ultimately drive the evolution of bipedalism, enlarged brains, and the complex technological and social behaviors that distinguish humans from other mammals. Australopithecus species living between 4 and 2 million years ago represent crucial steps in human evolution. These early hominins combined ape-like cranial features with human-like bipedal locomotion, allowing them to exploit both arboreal and terrestrial resources. Their brain sizes remain relatively small, comparable to modern chimpanzees, but their upright posture freed their hands for tool use and manipulation of their environment in ways that would prove revolutionary. The genus Homo appeared approximately 2.8 million years ago, marking the beginning of a remarkable expansion in brain size, technological sophistication, and ecological influence. Human evolution advanced during the Pleistocene with the development and spread of several hominin species. Early in the epoch, Homo erectus was the first of our ancestors to migrate from Africa, spreading across Asia and Europe starting around 1.9 million years ago. This species had a human-like body plan, a larger brain, and created hand axes as part of the Acheulean stone tool industry. The evolution of increasingly sophisticated tool technologies allowed early humans to exploit resources that were unavailable to other mammals. Stone tools extended the cutting and processing capabilities of human teeth and hands, while the control of fire provided access to new food sources and enabled survival in climates that would otherwise have been uninhabitable. These technological innovations represented a new form of evolution, cultural rather than genetic, that could occur within single generations rather than requiring thousands of years of natural selection. The migration of humans out of Africa and their subsequent colonization of every habitable continent represents one of the most significant biogeographical events in mammalian history. Unlike other mammalian species, which typically required millions of years to adapt to new environmental conditions through genetic evolution, humans used cultural adaptations to rapidly colonize environments ranging from Arctic tundra to tropical deserts. This unprecedented expansion brought human populations into contact with naive mammalian faunas that had no evolutionary experience with human predation. The impact of human expansion on mammalian communities was immediate and devastating. The correlation between human arrival and megafaunal extinction is one of the strongest patterns in the paleontological record. In Australia, human arrival approximately 50,000 years ago coincided with the extinction of giant kangaroos, massive wombats, and predatory monitor lizards. In the Americas, human colonization around 15,000 years ago was followed by the rapid extinction of mammoths, giant ground sloths, saber-toothed cats, and dozens of other megafaunal species. The hunting technologies developed by Pleistocene humans were unlike anything previously evolved by mammalian predators. Projectile weapons allowed humans to kill prey much larger than themselves from safe distances, while coordinated group hunting strategies enabled small human populations to overwhelm even the largest mammals. Fire was used as a hunting tool to drive prey and modify habitats on landscape scales, fundamentally altering ecosystems in ways that had never occurred in mammalian evolutionary history. The psychological and behavioral capabilities that enabled human success also distinguished them from other mammalian species. Advanced language capabilities allowed the transmission of complex information across generations, creating cumulative cultural knowledge that far exceeded what any individual could discover in a single lifetime. Abstract thinking and long-term planning enabled humans to anticipate and prepare for environmental challenges rather than simply responding to immediate circumstances. The domestication of other mammal species represents humanity's most direct intervention in mammalian evolution. Beginning around 15,000 years ago with the domestication of dogs, humans began selectively breeding other mammal species to enhance traits beneficial to human societies. This process created domestic animals that were fundamentally different from their wild ancestors, not just in appearance and behavior, but in their evolutionary trajectories. Dogs represent the most successful example of human-directed mammalian evolution. From wolf ancestors that were already among the most behaviorally flexible and intelligent mammals, humans created hundreds of distinct breeds adapted to specific functions. Some breeds were optimized for hunting particular prey species, others for herding livestock, and still others for companionship and protection. The global population of domestic dogs now far exceeds that of wolves, representing an evolutionary success story that would have been impossible without human intervention. The domestication of large herbivorous mammals, cattle, sheep, goats, horses, and pigs fundamentally altered global mammalian communities. These domestic animals achieved population sizes and geographic distributions that far exceed those of any wild mammal species. Cattle alone now outnumber all wild large mammals combined, representing a massive shift in global mammalian biomass. The environmental impact of these domestic herds has been enormous, contributing to habitat modification, soil erosion, and greenhouse gas emissions on scales that affect global climate systems. The agricultural revolution that began approximately 10,000 years ago accelerated human environmental impact and further altered mammalian evolutionary pressures. The conversion of natural habitats to agricultural landscapes eliminated the resources needed by most wild mammal species while creating new opportunities for those capable of exploiting human-modified environments. Some mammals, such as brown rats and house mice, became so successful in agricultural settings that they achieved nearly global distributions as human commensals. The Industrial Revolution of the past few centuries has accelerated human impact on mammalian evolution to unprecedented levels. Rapid habitat destruction, pollution, climate change, and direct exploitation have created extinction pressures that exceed those experienced during the late Pleistocene extinctions. Many mammal species that survived the original human expansion now face threats from industrial-scale environmental modification that may complete the process of megafaunal extinction begun 12,000 years ago. Urban environments represent entirely novel ecosystems that have emerged only in the past few centuries but already support distinctive mammalian communities. Urban-adapted mammals like raccoons, coyotes, and various rodent species demonstrate continuing mammalian evolutionary potential, developing behaviors and sometimes physical traits adapted to city life. These urban populations often exhibit behavioral flexibility, problem-solving abilities, and social structures that differ significantly from their rural counterparts. The conservation movement represents a recent but crucial development in human-mammal relationships. For the first time in human history, significant efforts are being made to preserve wild mammal populations and their habitats. Conservation successes with species like gray wolves, brown bears, and mountain gorillas demonstrate that human activities can reverse extinction trends when sufficient resources and commitment are applied. However, these efforts require enormous investment and often succeed only in maintaining small, manage populations rather than restoring historical ecosystem functions. Climate change, driven by human activities, now threatens to reshape mammalian communities on scales comparable to the natural climate changes that drove previous extinction events. Rising temperatures, shifting precipitation patterns, and extreme weather events are altering habitats faster than most mammal species can adapt through natural processes. Arctic mammals like polar bears and caribou face particularly severe challenges as their ice-dependent habitats disappear, while tropical species confront novel temperature and precipitation regimes that exceed their physiological tolerances. The current rate of mammalian extinction is estimated to be 100 to 1,000 times higher than natural background rates, leading many scientists to conclude that we are experiencing a sixth mass extinction event comparable to those that occurred during major geological transitions. Unlike previous extinction events caused by asteroid impacts or volcanic eruptions, this extinction is being driven by the activities of a single species, humans, creating unprecedented challenges for conservation and ecosystem management. Yet human influence on mammalian evolution is not entirely negative. Medical advances have eliminated diseases that historically limited mammal populations, while captive breeding programs have saved numerous species from extinction. Genetic technologies now allow direct manipulation of mammalian genomes, potentially enabling the resurrection of recently extinct species and the enhancement of conservation efforts for endangered populations. The extinction projects aimed at reviving mammoth populations using genetic engineering techniques represent the ultimate expression of human control over mammalian evolution. The relationship between humans and other mammals continues to evolve in unexpected ways. Wildlife corridors and habitat restoration projects are creating new opportunities for mammalian dispersal and population recovery. Urban planning increasingly considers wildlife needs, leading to the development of green infrastructure that supports both human and mammalian communities. Ecotourism has made wild mammal populations economically valuable in ways that encourage their protection rather than exploitation. The future of mammalian evolution will be largely determined by human choices made in the coming decades. Current trajectories suggest continued habitat loss and climate change that could drive additional waves of extinctions, particularly among large-bodied species that have already been reduced to small, fragmented populations. However, growing awareness of biodiversity loss and advancing conservation technologies provide hope that the worst outcomes might be avoided. Understanding the human factor in mammalian evolution is essential for making informed decisions about conservation priorities and strategies. The same intelligence and technological capabilities that have made humans such a dominant force in mammalian extinction also provide the tools needed for mammalian conservation. The species that once cowered in the shadows of dinosaurs then rose to dominate terrestrial ecosystems as magnificent giants, now face their greatest challenge in the form of another mammal species whose own evolutionary trajectory has given an unprecedented power over the fate of all life on Earth. The story of mammals and humans is far from over, but its next chapters will be written by conscious choice rather than blind evolutionary forces, marking a fundamental transition in the nature of mammalian evolution itself. As we reach the end of our journey through 66 million years of mammalian evolution, we find ourselves confronting a profound paradox. The story of prehistoric mammals is simultaneously one of life's greatest triumphs and most devastating failures. From humble beginnings as small nocturnal creatures cowering in the shadows of dinosaurs, mammals rose to dominate terrestrial ecosystems with a diversity and magnificence that may never be equaled. Yet this golden age ended in catastrophe, with the greatest mammals our planet has ever known vanishing in what amounts to an evolutionary instant. The rise and fall of prehistoric mammals offers crucial insights into the nature of life itself. The explosive diversification following the dinosaur extinction demonstrates evolution's incredible creativity and opportunism. Given empty ecological space, life rapidly expands to fill every conceivable niche, creating forms so spectacular they challenge our understanding of what is biologically possible. The giants of the EOCENE, MIOCENE, and Pleistocene were not evolutionary accidents. They were the logical outcome of natural selection, operating in environments that rewarded size, specialization, and ecological dominance. Yet the very factors that enabled mammalian success also made them vulnerable to unprecedented challenges. The environmental stability that allowed millions of years of evolutionary refinement was not permanent. When rapid climate change coincided with the arrival of human populations, even the most successful mammalian lineages proved unable to adapt quickly enough to survive. The pattern of extinction that ended the age of giants continues today. We are witnessing a second wave of mammalian extinctions that echoes the events of 12,000 years ago, with the same size-selective bias toward large species and the same primary cause: human activities and their environmental consequences. The survivors of the first extinction crisis are elephants, rhinoceroses, great cats, and other large mammals, now face threats that may complete the process begun in the late Pleistocene. But the story of prehistoric mammals also offers hope. Life's capacity for innovation and adaptation, demonstrated repeatedly throughout mammalian evolutionary history, continues today. Urban-adapted mammals, conservation successes, and the remarkable resilience shown by some species suggest that mammalian evolution is far from over. The same creative forces that produce saber-toothed cats and giant ground sloths continue to operate, though in environments increasingly shaped by human activity. Understanding the rise and fall of prehistoric mammals is not merely an exercise in paleontological curiosity. It is essential preparation for the choices we face today. The magnificent creatures that once ruled our planet serve as both inspiration for what life can achieve and warning of how quickly even the most successful evolutionary experiments can end. Their legacy lives on in the mammals that share our world today, carrying forward the genetic innovations of 66 million years of mammalian evolution into an uncertain but potentially remarkable future. The age of mammalian giants may be over, but the age of mammals continues,